Alrighty, in this section we are going to build upon section 5.1 where we talked about the area under a curve. We have three basic things we want to accomplish in this section. We want to be able to convert Riemann sums to integrals. We want to be able to use our calculator to estimate integrals using Riemann sums, left, right, and midpoints, and use the properties of integrals. So let's start with the definition. A definite integral is equal to that limit as n approaches infinity, where we divide the area under the curve up into n subintervals. So it's a nice way of labeling that area under the curve. Some notation definitions. If we have the integral from a to b of f of x dx, this is called the integrand. A and b are the limits of integration. This is our upper limit, and this is our lower limit. Dx, the differential x, you learned about before the last test. It is the differential x, and I spelled that wrong, but it's also a reminder of what we are integrating with respect to. Differential of x. So it's a reminder of what we are integrating with respect to. We're integrating with respect to x in this case. Okay. So there's the pretty picture explaining that the Riemann sums take the rectangles and let the number of rectangles go to infinity. If the graph is entirely above the x-axis, then it's definitely defined as that area under the curve. If your curve goes down below the x-axis, everywhere it's below the x-axis, those numbers will be negative. So it's the net area underneath the curve. So what's beneath the x-axis is negative. What's above the x-axis is positive. If f is continuous on a closed interval or has a finite number of jump discontinuities, remember what those are, not infinite discontinuities, but jump discontinuities, then f is integrable on that closed interval and that finite integral exists. There is just the blue box definition, again reminding us that delta x is equal to b minus a over n. And this kind of shows us how we convert from Riemann sums to integrals. So you notice the n doesn't appear anywhere in the integral. That's because that n has gone to infinity as we convert. So a and b are the ends of the interval that we're integrating over. So they are what we use to get delta x. We used b minus a over n to get delta x. So we have the integral from a to b. The function stays exactly the same. The delta x transforms into a dx. So the sigma gets stretched out, s for sigma, into that long stretched out s, the integral mark, and we go from the smaller number to the bigger number, lower to upper limit of integration, the integrand. So probably one of the easiest questions you'll have on WebAssign. Something like example 1, where you just have to write down the integral that represents the Riemann sum. So we're integrating over the interval from 0 to pi. That comes from our a and b. F of x looks exactly like it does except we don't have the little sub-i's on there. Plus x, sine of x, delta x becomes dx. Told you it was easy. That's it. That's your answer. There it is in print. Okay, now I think that's enough for our goal number 1, converting Riemann sums to integrals. Let's go on to example 2. Well, we'll use the calculator to estimate integrals. So first thing I'm going to do is write down the integral that I'm estimating. It says to evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be right endpoints. So in the notation of our last section, we're calculating r sub 6, the Riemann sum, with 6 right endpoints. In integral language, we are calculating the integral from a to b of f of x, x cubed minus 6x dx. There we go. So in order to calculate this Riemann sum, we need a delta x. Delta x is b minus a over n. So it's a half. Now I am going to write down this Riemann sum exactly the way that I am going to plug it into my calculator. And I'm actually going to move it down a row because I write big. When we use our calculator, our index is labeled with an x. And x is always going to go from 1 to the number of rectangles. Now think about right endpoints. When we do right endpoints, we always want to start 1 delta x away from the starting point. So generically, it would be a plus delta x. Well, a is equal to 0 plus delta x times my index. And I'll do it where x is equal to 1. That'll give me f of a half. I'll do it with x equals to 2. That would give me f of 1. X equals 3. F of 3 halves. So it's exactly what I want to get my right endpoints. And then delta x is equal to a half. Now I just used f of here because I find it easier to put my function into my table and just use that instead of trying to type the function into my sigma. So let's do that first of all. Turn my calculator on, and I cheated and did it ahead of time. So when I hit my table function, edit function, it's already there. So yours may not be there, so take a minute, plug it in. Hit enter. Be sure you hit enter after you type it in, and then second quit. Get out of there. Then you need to press the math button. You'll see this. You have a choice. You can either arrow down to sum, or you can just press 5 after you press the math button. And then your little sigma appears. And I have it all written down, what I need in there. I want my x to go from 1 to 6. Now how do I get it to say f of? I hit table. Enter. Table enter makes the F and the opening parenthesis appear. Now, since my A in this case is 0, I can kind of be a cheater and not put it in there. So I'm just going to put 1/2 of x. Close my f of parentheses. So I'm doing f of 1/2 of x and then times delta x, which is 1/2. And I get negative 63/16. Now, when we were doing area under a curve, we never would have gotten a negative answer because we were just looking at areas that were above the x-axis. You can see if we look at the picture, there's a whole bunch of that picture that is below the x-axis. That is why we got a number that was less than 0, because all of these orange, yellow rectangles have negative areas. The blue has positive areas. Okay, so that's easy enough for right rectangles. Since I have it in my calculator already, I'm going to go ahead and write down my left endpoint estimate. X equals 1 to 6. Always x equals 1 to the number of rectangles. Now, left endpoint rectangles, our first endpoint should be A. So we're going to take delta x and multiply it by x minus 1. Okay, so if I put 1 in, I get 1 minus 1, I'm doing f of 0. 2 in, I put f of 1/2 times 1, so f of 1/2. It's exactly what I want. Those are my left endpoints. And then I also have to multiply by delta x. Now, one nice thing about using my calculator, I can arrow up, hit enter. I hit second insert, and I'm going to insert a parenthesis, arrow over, I have to press second insert again, minus 1. Now I have f of 1/2 times x minus 1. I need to close my f of parentheses, hit enter, and I get the left endpoint estimate of negative 135/16. So I expect the actual value lives somewhere between those. Can't be guaranteed that because it decreases and then increases, but I expect it lives somewhere between there. Next time we do an example, we'll write down some guidelines for how we do the Riemann sums on the calculator.